Let's move on to our last presenter, Dr. Masabo Malali, who from NYU Grossman School of Medicine, who will be presenting on machine learning approaches to classify HIV prevalence of communities using social, economic, and behavioral data in resource-limited settings.
Hello, everyone. So since I'm the last presenter, I hope I'm not going to make you sleep. So I'll try to, keep you active and enjoy this. All right. So my name is Masabo. I'm a research scientist at New York University. Today, I'm going to take you through how machine learning approaches can help us identify communities with high HIV prevalence from just socioeconomic and behavioral data, which are always around us. Okay, how can we leverage, especially in resource-limited settings, where biomarkers can become a little bit, limited, especially, because of, finances and stuff. Oh, thank you. This works. All right. So, as I said, what was the motivation? So, measures of HIV prevalence currently are used to help public health officials and researchers and policymakers monitor the epidemic, evaluate the impact of interventions, and assist in the identification of sites for HIV prevention trials. However, current estimation of HIV prevalence strongly depends on availability of HIV biomarkers, which are challenging and expensive to collect, especially in resource-limited settings. Okay, it may not make sense probably in some of the areas, but trust me, in areas, especially remote in sub-Saharan Africa, it can be a problem. But also, so some of the report from FIA surveys, which these guys do a lot of surveys around HIV, they've shown how difficult it's becoming to collect biomarkers from people. So can we now leverage on machine learning, artificial intelligence to do this? So this is our objective. Can we accurately identify communities? I already said that, so I'm not going to repeat myself. But specifically, I'm going to use partial least squares and decision tree analysis. Partial least square is simple, it's a linear regression analysis with multiple variables. The only thing which is different from linear regression for those statisticians is just that partial least square offers, feature reduction. So instead of relying on, redundancy of information within a data set, then partial least square can help you create components which is representative of the original data set without losing information. So that's what partial least square does. Then decision tree. I'm gonna walk you through this. So data, I have to talk about data. What data am I using actually in this analysis? So we utilize data from population-based HIV impact assessment, famously known as FIA surveys. Not fear like fear is, PHIA, so don't be scared. Conducted in Zambia and Kenya. So the FIA surveys are representative household and individual surveys that provide comprehensive data on socioeconomic and behavioral factors related to HIV. Individual levels data are collected through structured interviews, capturing information on demographics, HIV risk factors, and household characteristics. So it's a very rich data set. So, of course, once they go through the interviews, those people who consent, right, they collect biomarkers from them. So, and then you can have a lot of comparison from that. And actually, that's what we use to compute our HIV prevalence. So using this data set, we generated 3 distinct data sets, which I'm going to use for model training and testing. So the first one is going to be ZAMFIA. This is for Zambia. So FIA survey collected from Zambia. Then KenFIA. This is predictor variables from Kenya FIA survey. Then I combined the 2 data sets by taking common predictor variables between the countries and make one, data set. And as you all know, machine learning leverages on big data. So the more data you have, the better the model. So that was the motivation for Zakefia. So I'm calling it Zakefia. So from now on, once you start seeing that, that's what it means. As I told you, easy stuff. Machine learning is just a name, it's just statistics. So let's do this. So how did I generate predictor variables from FEAR survey? Actually, it was simple because our interest is more of communities, not as individual, like communities. So, and the way FEAR is calling them, so it's using enumeration area. So it's kind of like small communities within a community. And actually I've defined an EA, enumeration area according to FEAR. It's just a geographical area with 200 radius. This is used in urban areas, and for rural areas, they use a radius of 1,000. So within that, then that's the enumeration area. And whoever is falling in that, then is picked for, sampled for the interview. So for example, these are some of the questions actually they asked during that interview, which is part of the FEAR survey. So things like, have you ever sold sex for money? How many drinks containing alcohol do you take on a typical day, and so forth? Are you circumcised? So in my case, for example, using are you circumcised question, this is how we generate the predictor variable. So taking a sum of circumcised male in that enumeration area divided by the total number of males in that, So you see, I'm making epidemiologists happy. So as some of them, they'll be saying like, oh, machine learning, you just don't know what you're doing. No, we do, you see. Yeah. Okay. And then, of course, as I said, using FEAR biomarker data, that's how we generate a HIV prevalence of each enumeration area. So in each enumeration area, which now from now on, we consider it to be like a community, just for the sake of, showing proof of concept, but it can be a village, it can be a district, it can be, depends on how you're trying to do. Then we can calculate HIV prevalence of that. And then that's going to be our object going forward. And actually, during our calculation of HIV prevalence, as I said, making epidemiologists happy, we excluded HIV. Those who we didn't know their HIV status, they were not part of generation of predictor variables. And since our interest was to identify communities with high HIV prevalence, so we started with the threshold of 10%. So those which are greater than 10%, they were grouped in one class, everything else in another class. So those ones would be named as hotspot vis-a-vis, what's the opposite of hotspot? Cold spot. So yeah, but also we kind of repeated this by changing the threshold, 5%, 7%, and 15% while doing this analysis. Another thing which actually we included in our data set was the distance of each enumeration area to the health facilities. This is how we actually calculate that distance, because the good thing about FEAR survey, they also include geocoordinates of each enumeration area, okay? But also we also found in one of the published paper, like it has a geocoordinate of health facilities in sub-Saharan Africa. That was a very rich paper, and those geocoordinates was available for us to use, and we leveraged on that. Okay, now interesting part, model training. So how did we do this? So now we do have a data set with enumeration areas with HIV prevalence classified into two classes, with a threshold of 10%. So now we have two classes, those who are greater than 10% and those which are less than 10%. Of course, now we are using 0 and 1, 0 to represent communities with less than 10%, and 1 for communities with higher than 10%. Okay, of course, we then randomized when we are dividing our data set into training and testing, where 70% of the data set was used for training the model, and then the 30% was used for testing. And those are the numbers. So 70% of the Zamfir was, Zamfir actually they had 711 communities. So 70% of that was used for training. The remaining was for testing. The same goes for Kenfir and the combination of the two. I'm just showing you how this thing in just illustration, because some people, you know, they like illustration more than wedding. So yeah, but that's what it's doing. It's just saying what I just said there. You have a data set, then you divide it into training, then testing. So this is going to be out of, it's not going to be part of the training. It's going to be set aside. And this is recommended, especially if you want to see whether the model is overfitted or not. So at least test your model on the data set the model didn't see during the, because sometimes they can cram the data. Overfitting is simply cramming the data. It's cramming all the parameters. You ask it, then it's going to answer, and then you realize, oh, it's doing great. But in fact, no, it didn't learn anything. Just cram the data. So to avoid that, that's what you do. You take out a portion of the sample and then test it later. So the partially square model we trained actually was just 15 components. So components here, think about now originally these predictor variables are used to generate, let's say you have 100 of them, right? And then as you have seen, so for example, for Zamfir, we had 511 communities. So it's going to be a matrix of 511 times 100. It can go even beyond that, 200. Training such, to train a model using such a data set, it can be challenging because, you know, you have a lot of the combinations going to be a lot for the model to learn while you don't have enough data. So at the same time, you might have these predictor variables which really communicate similar information. So to remove that redundancy, that's why you have to perform partially square, you know. So what it does is just go through and see those variables which communicate similar information, they get grouped into one group, right? And then you kind of like analyze to see how much, if you create different groups, how much information are you going to lose, okay? So, and that's what this is showing me. So with that, I'm trying to see, okay, how much components can I generate from this data set before I train the model? So, and that's what you see from 0 to 50. That's the number of components from that data. And then from y-axis, is just showing you the variance, you know, you're going to lose. So you can see from here, once you hit, I think on 15, you start to plateau. So meaning the more, even if you go to 30 or 40, it doesn't make a difference because there's no much information you're going to lose. Okay. Oh, yeah.
If you want to, yes, just.
Yeah. Now this gives me freedom. Yeah, I love this. Okay, so that's what we do for partially square. So it's simply doing that. The rest is just make it look fancy, but it's nothing. And then for the decision tree, as you can imagine, so a tree has a lot of nodes, but you want to know how the depth of the tree should you go before you can start overfitting and something. So how do we decide the depth of the tree we want? So it's simply doing a cross-validation technique where you have x-axis. This is the number of tree depth, okay? And y-axis, that's the accuracy. Then you kind of see. So then the blue, that's the training curve. So it's you're training and then testing from the training data, the 70% I showed you, right? But then the validation accuracy is out of the training. So now this is going to try to show you. So you can see initially, this kind of like start going closer to the training. Then once you get to the depth of 3, kind of plateau a little bit. Then at 4, it's kind of like start to decline. So meaning if you train a tree beyond, which has a depth beyond 4, then you're going to lose the accuracy on the out of the sample testing. That's how we decide how deep the tree should go. So if you're wondering, like, what he's talking about trees, what trees is he talking about? So this is kind of like illustration of how the tree looks like. So you can start here is like where you start. It's one of the, trees. So like you kind of start from here. Everyone is here. And then you divide them based on this information. So this one, for example, the criteria with quintile, less than, 15%. So it's a measure of economic status. And then if it's true based on this information, come here. If not, then go on this, And then, okay, now once you're here, how about this is the circumcision status, okay, for male. So this is the proportion. If this one they agree, then okay, go here, come here. So that's how the tree works, okay? And the depth I was talking about is, okay, should we go beyond? So for example, like here and here, you can be tempted to go beyond. But the problem with doing that, yes, you're gonna make better accuracy for this data, but it's not gonna do better for the out of the sample. So it's a trade-off, okay? But there's some ways you can, avoid this by now random forest, there are different ways of doing this. Oh, okay. I'm told I have 2 minutes. So model training, again, this, I think I talked about this. We repeated the threshold. Another thing which we did, so after training the model, we just did cross-testing. So training on Kenya data, test on Zambia, and then train on Zambia data, test on Kenya. So the idea was, in case of those countries where they don't have this FEAR survey, can we leverage on, and see how? Actually, in machine learning, it's kind of we're just pushing harder for our model to see how it can do. But literally, you need to have representation of that data in your training set. This is just showing you how the metrics used to score the model performance. I have sensitivity, specificity, accuracy, and precision. I just wanted to show for those who doesn't know what that means, but then I'm gonna skip this. So these are the results. So generally, our models demonstrated robustness. So you can see the accuracy was, between 76, plus or minus 5 for all models and, settings and, especially when we did, out of the sample testing. Okay. Slightly random forest models kind of like outperformed partially square, but generally, especially on HIV prevalence of 15%. Otherwise, the result shows there's liability of these models to complement the current methods. Of course, this one is a busy slide, but the idea of this is if someone is doing machine learning, and especially the fact I'm doing binary classifier, would ask me to do, receiver operating curve, and that's what you're seeing. Literally, it's just showing you like the dot, that's the random estimator. Above, that's the model. So if it's doing above, then it's doing better. So the perfect one should be, closer to the angle, but this one is, so showing you how good it is as you change different threshold, especially when you're doing interpretation. And those are area under the curve. These are the results when we tried to change now Kenya to Zambia, Zambia to Kenya. Actually, yeah, you could see, the accuracy, was approximately 55. Sensitivity for test A and D, the definitions are here. So A, Zamfia to Kenfia, so like Zambia data to Kenya data. B is Kenya data to Zambia data. So, and C, so forth. So you could see in some of the tests, the accuracy was, especially specificity and sensitivity was impacted. But generally, it's okay. It's better than nothing, rather than like go with, when we don't have data, sometimes we just go with our intuition. But this one can help add that intuition when you don't have data. That's what it means. Can I finish on that? Yeah, so this is the important variable. We wanted to see how much which variable carried much weight in these models to perform what they performed. And for Kenya, actually, variable related to Protestants, this is the religion domination, got in relationship, financial support, married or cohabiting, living together, the proportion of people who are doing this, proportion of uncircumcised, proportion of people experience, physical and sexual violence, proportion of people who had first intercourse experience before age 15, and so forth. And that's for the Zambia side. So this found to be a very important variables especially for this analysis. Here's the conclusion. So the conclusion is our study has shown we can rely on this. Actually, this is the proof of concept. Much has to be done. Okay. We relied on fear survey, but probably now we are living in a rich data environment. So census data, which are, easy to collect, they're already done with our countries, could be leveraged to do this and keep on doing things like this. So this is kind of like work in progress, and set a precedence. Like we can rely on this to leverage and probably complement the method we have. Thank you so much. These are the people I would love to acknowledge. Without them, this work wouldn't be here. So thank you so much. And thank you for allowing me 1 extra minute.
Thank you. Thank you for the fantastic presentation. Do we have any questions in the room?
All right. Thank you for the great talk. So in your method, you talked about things like hotspots, and then you had different thresholds there. 10%, I think that was 5% or 7.5.
Yes.
Are those attached to any strategic goal, or was this for you just set them?
No.
Because I'm asking because of the falling HIV prevalence in most sub-Saharan African countries. So are they attached to specific goals, or how did you come up with
No,
those
this was random repeat. And the idea is simple, because hotspot could be subjective, right? Exactly. So in one country, let's say 5% could be, higher. In another country, they're still struggling with more than 5%.
Exactly.
In some point, probably 1% would be greater than 1% is a hotspot. But the idea was to change threshold and see how reliable this model can be. Is the threshold going to be going to affect the performance of the model? Because literally, the best model could have been a regression model, but you need more data to do that, to train the model. So we don't have. So instead, we are choosing to go with classification. And then that's how we have to change the thresholds.
All right. Thank you.
Thank you. Now I'm happy, because otherwise I was like, wait a minute. No one was listening.
Ordinarily, I would assume demographic would play in both Kenya and Tanzania. And Zambia. But I noticed it's not in Zambia. What could be the reason? Well, I know AI sometimes limits us, but what could be the other reason?
What do you mean by demographic?
So in one of the slides, you gave us the important variables. And you notice we don't have any demographic variable for the Zambia.
No, so this one is not showing everything which was included in the analysis. Of course, another thing which actually was very interesting is the same people who are doing this survey, but then in some of the countries, some of the questions was altered. And that's why, when I was combining the data set, the third data set, some of the questions was removed, that one. But second, what you're seeing here is not everything these are just important variables. But otherwise, there's more than 100 variables which was there. So demographic, for sure I can confirm, is there. It's something which they capture in both countries. It's just that this was found important in Kenya, but not in Zambia. For some reason, that's one thing which machine learning offers. Why do we see this in Kenya and not in Zambia? What's going on? Then you can go down and start looking. Yes, it can be hallucinations. That happens in machine learning, but it's a point to start digging and see what is going on.
Thank you. I have lots of questions actually, but I'll try to keep it limited. One question was whether you considered adding other countries so that you have an even bigger data set. Another question was when you were sort of looking at these hotspots, I wondered whether you looked at or considered doing relative hotspots so that, you know, for, as you say, HIV prevalence varies a lot from one country to another. 10% might be a big problem in one country or relatively low in another. So you could sort of, I wondered whether it would make sense to look at the relative nature of the hotspots rather than using the same absolute value across all countries. Then I also had questions about whether you could pull out the sort of relative contribution of each of these different important variables, but you just see what you have time to ask.
Yeah, actually, starting with the second one, that's a great question. And that's something we've been thinking, and probably in ongoing, you know, analysis, we'll start incorporating that and start narrowing down even within, you know, certain community. Then you have to narrow down and start seeing, you know, because as you said, there's a lot of dynamics. At the point of country, yes, it's like now you're getting in my head. Yes, we're doing that, but again, but so far this is what we had analyzed. As you can tell, one of the things which initially we wanted to make, as I said, kept an epidemiologist happy, wanted to generate these variables manually, trying to make sure like we can start, you know, scale up with other country. Though we are seeing these variabilities in terms of it, you know, so then that can impact, but that's where we're going. It's something which we are thinking of doing. It was just, yeah, okay.
Okay, let's make this a little quick.
Thank you for making this so interesting. I was just wondering why you limited it to 2 models. You know, if you're familiar with the no free lunch theorem in machine learning, you try various models. And so even, for instance, the PLS that you use, you could have maybe considered Lasso or Ridge, you know, if you wanted to penalize some of the variables. So that's one question. Then you kept on interchanging random forests with decision trees. So it would be nice to let us know which one did you use particularly. You know, random forest is an ensemble method and a decision tree is not. So which one did you use, and then why did you limit it to just 2 models?
Thank you. Actually, those are great questions. So why 2? So first of all, the motivation, actually, that's why we didn't even see any neural network model here. One of the motivation was to start simple so that you can understand what is going on and explain. The problem with this, you know, high, especially neural networks, there's a lot of things we can't explain, especially if you want to understand the important variables behind the scene. What is, you know, so that's why that was the motivation. So partially square, you know, as one of the methods which really heavily, you know, it's on a linear relationship which is going to capture. Okay, so, but it's easy to communicate to people. It's just regression analysis. We're just adding a component of feature reduction. Decision tree, the good thing about that, it brings in another non-linear relationship-ish on the analysis. So it's kind of like a way of trying to go beyond linear relationship and capture something beyond, but also we can explain to people and they can understand. And then at least we can see what is going on before we can go full-fledged, like trying to go with the high-level machine learning techniques. Decision tree or random forest. I use random forest, but random forest, as you said, is just a combination of decision trees. So if I want to explain, at least someone understand what I mean by random forest, I just have to pick one tree, show this is what decision tree means, then random forest is a combination of many decision trees, and then it's an ensemble is going to be the output of random. So that was the motivation. Yeah, of course, we can consider, of course, someone can come and challenge, okay, probably we can get beyond 75, 6 years short, but we can try. There's a lot of things you can do and change and see how things can, yeah. If at all your interest is to classify, but for us, we wanted to see what are the predictor variables behind. So that's why we wanted to, until it's starting simple. As you know, my former professor actually who trained me used to say that, you know, if you have good data, simple methods can do better. Like you don't even need to go to higher level machine learning techniques. First understand your data, make sure you know what you're doing, and then you can start building upon. Yeah.
Okay, thank you for that presentation. I just got curious about the variable importance.
Yes.
Given that machine learning, when you run it every now and then, the variables keeps on changing. And just reflecting on that question, which we saw that demographic variables are missing. Maybe could it be because of those variations we normally have? And then if so, then how can policymakers be informed with these variables if we say they're important, but the next time we run them, they are not? Thank you.
Thank you. Actually, that's a great question, because what I'm showing here, these are important variables across different threshold. I told you I changed threshold 5, 7, 10, 15. So these were constantly happening in those, but also 2 models, partially square random forest, right? So these were again, like consistently happening in both models, different model architecture with different mechanism, then changing thresholds, but still these were constantly. So I would say this was out of scrutinization, you're saying. But yes, that can happen, but this is at least, you know, went through that filtration to the point it kept on happening.
Thank you. Can you all please join me in thanking our fantastic presenters this afternoon? And thank you all for attending and your participation.